This video will introduce how region of interest-based encoding, implemented with the Zynq UltraScale Plus MPSoC Video Codec Unit, can be used to maximize broadcast bandwidth. First, we'll briefly outline the broadcast bandwidth problem. Then we'll cover region of interest-based encoding as a potential solution and how it's done with the Xilinx Video Codec Unit. Going forward, we'll use the abbreviations ROI for region of interest and VCU for Video Codec Unit. We'll introduce the Zynq UltraScale Plus MPSoC VCU ROI reference design. We'll show a demo of VCU ROI encoding on the Xilinx ZCU106 evaluation board, and point you to resources for getting started. Let's talk about the advancement of video resolution and its implications. In just a few years, we've seen the race from 720p to 1080p to 4K and beyond to enable the display of crisper frames on larger and larger screens. Today, most TV and camera manufacturers advertise 4K resolution. But the problem is that 4K requires 4 times the data rate of 1080p video, which means a significant amount of storage or streaming bandwidth. One way to tackle the problem is to improve video compression. In certain camera applications, within the field of view of the camera, some areas are of greater importance than others, and some areas are really of no interest at all. The areas of importance within the scene can be exploited to improve the compression efficiency, which helps in reducing the storage or streaming bandwidth needs. Examples of applications where we have these areas of greater importance or regions of interest are video conferencing, video surveillance, and news broadcast. So what is ROI-based encoding? ROI-based encoding algorithms exploit differences in the importance of regions within a scene or a frame. They provide more quality to regions of interest, like faces or people, and reduce quality to regions of lower importance, like backgrounds. This reduces the overall bit rate of the content, which reduces streaming and storage costs. Consider the example of video conferencing. Participants are of greater interest than the background. You would have a video camera pointed at your participants who are the ROI. You would have an ROI detector and tracker to extract the coordinates and track ROIs among the different frames, because your participants will be moving and not static. The extracted coordinates along with the importance would be provided to the encoder. Then, ROI-based encoding would allocate more bits to the identified participants and less bits to the background or static objects by assigning the quantization parameters accordingly. You could then provide a significantly better viewing experience on a lower bandwidth network. The Zynq UltraScale Plus MPSoC Video Codec Unit supports ROI-based encoding for both the AVC and HEVC standards, so the ROI-based encodes are fully compatible with other compliant decoder vendors. The user can identify multiple ROIs within the same frame in programmable logic. The smallest ROI for the VCU is the macro block size for the codec standard. The VCU gives you the flexibility to assign different quantization parameters based on the needs. VCU ROI-based encoding is supported for multiple stream scenarios. It is supported only for frame-based encoding and not slice-based encoding mode. Next, we'll talk about the VCU reference design that demonstrates ROI-based encoding on the VCU and uses the GStreamer framework and software. To demonstrate ROI-based encoding on the Zynq UltraScale Plus MPSoC EV device, we have a reference design that uses 2 ZCU106 boards. ZCU106 board 1 is responsible for the video capture, encoding, and transmission. ZCU106 board 2 acts as the playback device and is responsible for the decoding and display. Both boards are connected via Ethernet cable. A camera sensor FMC module is the live video source connected to ZCU106 board 1. Once the 4K video frame is captured from the camera sensor, the data gets pre-processed and fed to the Deep Learning Processing Unit, or DPU for short. The DPU uses the dense box network to detect faces within the frames. Once faces get detected, the DPU provides the coordinates of the faces along with the raw video data to encode. The encoder uses this information and compresses it to 2 megabits per second accordingly. Once the stream is encoded, it'll get packetized into RTP packets and streamed via 1 gigabit Ethernet to ZCU106 Board 2. Board 2 receives the live compressed stream, depacketizes, decodes, and displays the video on the connected monitor, where you'll see the difference in the quality of faces compared to other regions within the frames. By using the ROI encoding feature of the VCU, a user can transmit 4K resolution at a lower bitrate while maintaining the quality of the important region. Earlier, we covered that the Video Codec Unit in the Zynq UltraScale Plus MPSoC can support multiple ROI. How would one compute the theoretical maximum number of ROI for a reference implementation? That would be the artificial case of having a full screen of exactly minimum-sized, adjacent, non-overlapping faces. Factors to consider are the resolution of the video input to the system. In this reference system, we're capturing UHD 4K P30, the macro block size. For H.265 on the VCU, that's 32 by 32 pixels. The image resolution presented to the DPU. The DPU is running the dense box 640 by 360 model in our reference design. The minimum face detection size for the DPU, that's 10 by 10 pixels. Considering this combination of input resolution and macro block size versus the resolution presented to the DPU and min ROI face size for the DPU, our theoretical max bounds will be based on the DPU portion of our system. So the theoretical maximum detectable regions of interest would be the most 10 pixel by 10 pixel non-overlapping faces you can fit into 640 by 360 pixels, which is 2,304. Here you can see the benefit of VCU ROI-based encoding. On the left is a video compressed to 1 megabit per second. On the right is a video also compressed to 1 megabit per second, but where more bits are used for the ROI and less for the background. The improvement in face quality is very noticeable, while the impact of reducing background quality is minimal. To get started with the VCU ROI reference design for the Zynq UltraScale Plus MPSoC, visit wiki.xilinx.com and search for VCU ROI to download the ROI-based encoding design files. Check out our videos explaining the hardware and system architecture and the software architecture of the VCU ROI reference design. For information about the ZCU106 board, visit xilinx.com/ZCU106. For further information, please contact Xilinx Sales.